sharing. Now I want to introduce Jonathan, who is going to, well, tell us some really neat things about the internals of macOS. So again, please no photos, but round of applause for Jonathan.
Okay, hi everyone. Yeah, nice to see you all. It's been a while since I've been to OBTS, I think since the first one. So hello to all, hello to anybody tuning into the live stream, or, whoa. Hello? Okay, yeah. So anyone tuning into the live stream, we're over the pond, even though it's awful early, I guess. My talk is about XNU, and specifically not just XNU, but rather all of the hardware features that Apple has put into iOS, and really Apple Silicon, if you think about it, because it's coming to the Mac, especially now with M5. And how they've evolved and how they've basically forced a redesign of XNU to the point of almost making it little again, in the sense of its own microkernel origins. The required blurb about myself, I don't have too much time. I am a founder of TG, Technology Geeks, who are a training and consulting company. Thanks to Patrick here, I did training after a long time for OBTS as well. And whatever, right? Expert training, expert internals, whatever. I'm also a founder of Dataflow Forensics, which is a sub-company of Dataflow Security, where we basically leverage all that information and all that internals expertise into finding APTs on devices, leveraging also unique abilities and exploit techniques in order to get out of the sandbox and therefore run basically a lot of the tools that you may know already, like Process Explorer and stuff like that, and get that unparalleled diagnostics data. I also wrote a bunch of books a long time ago, and there's another book that I just brought out, but there's no time for product placement, so let's move on. This talk is basically, as I said, about Apple's really unique position. And we're all, Apple fanboys here, so I'm not going to go and extol how amazing Apple's OSs are, but they really are. And what's even more amazing is that Apple controls the full stack. And that gives them the unprecedented and really unrivaled ability, as opposed to, say, Android, where they can not only know exactly what code is running on their device, and with code signing and all sorts of iBoot, secure boot, can ensure that nothing out of what they allow goes on the device, but also they're able to actually change the silicon. And this is something that's really, really big, especially now that they're effectively moving out of Intel. I'm assuming that by Darwin 26, it's all going to be over and there's not going to be any Intel Macs supported anymore. And so this gives them the basically complete control of the full stack, including the hardware, and those particular features are something that I'm going to be discussing here. They give you different abilities that then, coupled with their amazing software drivers, enable them to really do stuff that nobody else can and really would take the rest of the industry a lot of time to catch up with. Now, this also comes at a certain price because those Apple premium devices, like the iOS ones, are obviously the highest profile targets for APTs. So it's basically where attackers break into their systems and then they start devising all sorts of countermeasures. And it's the usual cat and mouse game where mitigations breed all sorts of bypasses, breed all sorts of other mitigations. Only in the case of Apple, it's been narrowly and basically very reliably reducing the attack surface to the point where it's getting harder and harder still. Now, if we do the really, really quick evolution of jailbreaks, if we go all the way back to the good old days of iOS 5 and before, there wasn't really much to jailbreak. As soon as people got any type of code execution on the device, which was usually back then either installing an app or going through Safari, they would be able to just get root. And at that point, all it took to disable the so-called mandatory access control framework was to just write to some sysctl, like a sysctl, security mac, proc enforce, vnode enforce, that's it, you're done. And so, AMFI and the sandbox would just effectively be neutered at that point because they'd still be there, but nobody would care about them. Nobody would actually call their hooks, and that's that. So Apple said, okay, let's not do that. Let's make them read-only. And that really was a landmark because around iOS 5, that's where jailbreakers took the fight to the kernel. And that's where we started looking at all sorts of kernel read writes. And that's where the by now legendary TFP0, which is Task for PID 0 patch, came into being and became its own little kind of like a meme thing. TFP0 means that if you've got Task for PID, which given a PID, like a process identifier, gets you the send write to the task port, in plain terms, complete control. It also works on 0, and even though Apple put a specific check that says if the PID is 0, then just return, it was trivial to just change that and just basically make it into a compare branch not 0, just to flip through, and it then never branches. And it's funny because, that persisted for a very, very long time. Rather than do some defense in depth, which, they would eventually do in like iOS 12, it was easy by then to patch that. So this whole area was like between 5 and I want to say iOS 9 or so, where kernel patching was like all the rage. And there was something called KPP, which I'll briefly introduce, but it was really a sham. It was not even worth discussing much, and because you could also race it. Also, back then was the golden age of code signature bypasses, which unfortunately or fortunately, you decide, ended with effectively, I want to say 9.2. That was the last known actual code signing that did not involve any type of kernel patching. And that's also why, not surprisingly, we don't have any more of those untethered jailbreaks, where the device would just reboot and automatically go into a jailbroken state. Now, iOS 10 and also the iPhone 7, the A10, were really the first time that Apple introduced some unique security feature called KTRR, which we'll talk about. But then the big revolution came with iOS 12, which is the A12 and such. So back in iOS 10, you could still do stuff. You couldn't patch the kernel, but there was plenty of stuff to patch. And back then, security paragon Ian Beer, who's probably floating around here somewhere, and he's giving a talk tomorrow, right? So basically, he just went with Project Zero, and every couple of weeks, every couple of months, he just give you a nice little write-up. And unlike other Project Zero write-ups, which is yeah, there's a bug, there was 45-minute disclosure, and they patched it, and don't worry about it. With Apple, it was more oh, wait, here's a TFP0. Go ahead and run this. It's on GitHub. Go compile it, and, make your own jailbreak, basically. So that was the case back then. And this persisted until around, I want to say, Async, which was I want to say 11.1. He probably remembers better than me. And that's when Apple really started changing the field. And that was with the introduction of PPL, which is going to take a large portion of this talk, with also its backing feature, its backing silicon feature, which is called APRR. The other thing, which definitely was a big deal, and also we'll mention briefly, is the whole idea of PAC, which by now in these sessions has been basically in every single talk, including Lucas's just now, was mentioned, because that is a very big deal, without which basically everything falls apart. Now, this continues, and in iOS 15, we've got read-only zones, and that is meant to extend KTRR so that it's not just the kernel text read-only region, but it's also all sorts of dynamic data. For example, process data or, entitlements, code signing blobs, and things that are kind of you can think of it as a write once and then never touch it, or at least don't touch it outside a trusted path. And this evolution continues with lockdown mode, which is actually, underlined here just to make me, remind you that if you've got an iOS device and it doesn't use lockdown mode, then it's a freaking death wish. Basically, if you can, please, please, please enable lockdown mode right now. It hampers your UX. Oh my God, no, you can't preview things. But you know what? You can't also zero-click things, which is better. I mean, I'm willing to do that. So lockdown mode and, of course, developer mode, where development mode basically, I think there's a presentation on that too. Basically, what it does is to make sure that some debugging entitlements, and in fact, debugging functionality, is supposed to be neutered and not available unless the user really, really wants it. And then this continues into iOS 17, and we're talking at this point in the A15s, where we have GXF, the guard execution feature, and this is something we'll really talk about a lot here, and culminating with exclaves, and that would have been it, but then Apple, has to do something new and exciting, so now we've got the so-called MIE, which is really empty, whatever. So that's going to be the focus of our talk here, and we're going to go into these in a little bit more detail, however much the time allows. So it starts with KPP, the kernel patch protector, which, as I mentioned, is a very, very rudimentary protection. This is something that you can see in the sources of XNU, but it's effectively dead. This was the one time Apple went and tried to do trust zone. So if some of you don't know what trust zone is about, don't worry about it. It is, however, still the linchpin of Android. And really, TLDR, it's essentially a secure compartment. So it does kind of inspire later on GXF, but GXF is a totally different implementation. The main thing about Trust Zone is that it is effectively, if you remember your ARM64 basics, you've got the ARM exception levels, And you've got user mode, which is, of course, EL0. And you've got the kernel mode, which is, of course, EL1, although GNU now runs in EL2 as well. EL2 is traditionally your hypervisor. And EL3 is your, effectively what they call the secure monitor. And traversals can be done just like from EL0 to EL1 is an SVC. You have an EL1 only to EL2. That's an HVC hypervisor call. We'll see that later as well. And we have EL1 only or above, really, but not EL0 to the secure monitor, which is SMC, the secure monitor call. The problem with that is that obviously you can patch out the secure monitor call. And so Apple contrives this type of idea called KPP, the kernel patch protection, where periodically you piggyback on an interrupt, because EL3 can gather or can claim the interrupts from EL1. And then basically upon interrupt, they run some hash on the pages that are supposed to be read-only. And it's really very rudimentary. It's a Blake hash, which is like super fast and like super efficient. And if there's any mismatch, then they just basically panic you. So on boot, when the kernel finishes fixing up all sorts of stuff in its data const, or if it's like, of course, a text that doesn't need to be modified, then they just take hashes of everything. And then they put those hashes, it's called a machine lockdown. It's via SMEC 2048 back then, and that's that. Now this is nice, but yeah, it really doesn't work. So then they bring something better called KTRR, the kernel text read-only. And this is the first time we actually see Apple-specific silicon registers. And this is something that's going to permeate this talk, where there's always some type of custom implementation-defined register. So going into ARM assembly a little bit, there's two instructions, MSR, MRS. Two machine-level instructions. MSR is like to set the register. MRS is like to read the register. And they're all special registers. In other words, they're not your standard things that you see in like a panic report, maybe, but not like in a user mode crash report, and not in those general X0 through X31. So in this particular case, these are registers that either ARM provides for you, like TTBR, VBAR, TPIDER, that kind of stuff, or there could be custom silicon implementation, and Google does some of those in their Pixel, and Samsung certainly does, all throughout Exynos. But of course, Apple does that as well. And Apple starts here with basically 3 registers, which are given the name, and we know the name because the source is, surreptitiously leaked in 6153, surprisingly enough. And so they didn't redact, and so we know they called them KTRR back then, lower EL1, upper EL1, and lock EL1. The idea is very simple. You MSR the base of the address that you want to lock at the first one, the lower, and then you want to do the base in the upper, so you get this range. The range obviously has to be contiguous. It's between the lower and the upper. And so you can't really say, well, you know what, there's another segment. Too late. That's why also in the kernel cache, they have this type of thing called last, and then you know where the range is. They have like a fake segment called last. And then once you're done and you're happy with it, the machine lockdown, rather than calling a SMEC, like SMC 2048 that it would have done, actually calls on the other register here, which is C22, named the KTRR lock. And this is a write once register. You write the value 1, that's it, you're done. And you cannot write the value 0 in any way whatsoever. Now, KTRR is definitely considered to be, the substrate without which everything also would fall apart. It's much, much, much stronger than the case of trust zone that is still used to this day in Android, because basically you can't race it. To this day, as I say here, it's mostly unbreakable, with the exception of, where is Brandon the Breaker, where are you? Yeah, I thought he was here. But yeah, he's like, he used to work for Project Zero, and then basically he created this really, really cool idea of build your own iOS kernel debugger. I think I had linked it somewhere here. Yeah, it's called KTRW, and really an amazing piece of work. But of course, it's something that hinges on the fact that Apple left CoreSite open, and that's fixed. So following, I want to say, iOS 11 something, there's no way to deal with this as well. And so this is, again, the baseline for us, and we can assume at this point that unless somebody's got a crazy O-day, which is not something you'll hear about because this would mean something that effectively, makes the kernel read-writable again, then you can basically say that even an arbitrary kernel read-write is not really so arbitrary anymore. It's read-write, yes, but it's only for readable, writable data, and it's outside the kernel text and the data const. So this is a huge step, but not good enough, because there's all sorts of data that gets written once, and then, because it's written once, KTRR can't lock it anymore. So, it doesn't matter how many times you write it. It matters that whether it's writable and then you can just, during boot, seal it. In other words, apply the lockdown on. Or if you can't, then just you can't, and that's done. So Apple finds a very, very clever approach to this. And this is something they call the page protection layer. And this effectively becomes their go-to for basically everything. It's introduced in the A12 chipset, which also, by the way, upgrades the boot ROM and blocks checkrain, if you guys know about the very infamous boot ROM exploit by then. And so it's kind of like those silent updates, and it's in an XR or XS that makes you think it's not such a big deal or not such a leap. But really, if you think about it, this was their most serious model basically ever, because they introduced this page protection layer. It hinges on PAC. Okay, so without pointer authentication codes, it is not going to work because it introduces this idea called a trusted path. In a trusted path, we have access to certain registers or certain, Apple dark magic that enables you to perform the feature in silicon and potentially, if you need to, disable it, re-enable it, and such. Now, of course, if the attacker can get arbitrary kernel code execution, then they could follow these exact same paths. So the idea is to make those paths really, really secure, and that hinges on the fact that you don't have kernel code exec. And PAC effectively in kernel defeats kernel code exec. Now again, there's a little star here about the Rumsfeldian unknown unknowns. We don't know if there's any kernel PAC bypass in kernel. But the above-mentioned Bran, after he posted in Google Project Zero about his own experience with PAC, mysteriously disappears, gets assimilated by Apple, and, that's it. And suddenly, nobody ever talks about PAC, and presumably whatever he knew, he helped them with. Brandon, if you're here, again, I'm sorry for convincing you. Sorry, that was a mistake, but whatever. And so basically at that point, that's it. PAC in kernel is considered to be a done deal. And the operational assumption is that if you're a jailbreaker / APT developer, and it's a kind of like shady distinction there, then basically that's not going to be the approach you're going to look at. And so you have to confront the PPL head on. And so you have to think of what becomes now the so-called PPL bypasses. With the PAC in user mode, not so much. PAC in user mode, there's still bypasses. Usually that hinges on the fact that in user mode, you do have dynamic pointer signing. The usual culprit is like DL-sim, which DL-sim gives you, DL open DL-sim. You open the dylib, you open like some framework library or some system library, and then you have to sign pointers. And every now and then there are these bypasses which either stem from DILD itself, greedily signing whatever you throw at it, or via all sorts of clever ways that eventually boil down to Objective-C runtimes. And not to upset my host, but Objective-C, in terms of security, is pretty much of an anathema. All these powerful reflection methods and all the calling the selectors and stuff like that also means that at the end of the day, there's no real vtables, but everything is done dynamically. When it's done dynamically, it also implies that, yeah, you have to get the pointer, but wait, we're in a PAC system, we have to sign the pointer dynamically as well. So some of you may be familiar, but there's NS expressions, NS predicates, and this whole thing could fill a talk by itself. Now, the thing about this PPL thing, the page protection layer, is that it also shows you, in some respects, how well XNU is designed. Not to go too much back in history and nostalgia, XNU was founded upon Mach, and Mach had this idea of being basically hardware agnostic as much as possible, running back then on a PPC or on a Motorola, if everyone remembers 68K. And so basically what they do there is to use the layer of XNU called the PMAP. For those of you not into kernel, this is actually something that's covered in one of my books in Moxie, Volume 2, that talks all about the kernel. And so there's the gist of it can be summarized in this slide. In user mode, you're probably familiar with VMAP, also possible with process, the PID regions. And fun fact, up until Darwin 23, process 0 regions showed you the kernel regions with no KSLR, whatever. That was a long-standing ODE for so long. But then basically what it is it gives you those regions. What's a VM region? A VM region basically translates to the Mach VM region, which is the APIs that Mach still used. And internally, it's a VM map entry, where a VM map itself is like your entire address space. And any one of those V8 maps is essentially contiguous regions. So think about anything you do in nmap, or maybe lower level mock VM allocate. You get a contiguous region, which is virtually contiguous, not physically, right? And then what you have there is, a set of protections that apply. And at that point, you can map this blob of memory, and you can move it around, and you can share it, and you can do all sorts of good stuff with it. Underneath it, it has to somehow talk to the hardware. And so if you're still an Intelite, not to say Luddite in this case, then you're looking at CR3, which is the control register 3 that holds your page table index. If you're looking at ARM, you're looking at TTBR, right? TTBR, there's EL0, there's EL1, and so there's something that needs to translate the access, what you would normally call V2P or P2V, which is virtual to physical, physical to virtual. And the way that's done is through this PMAP, which further goes to something they call internally ML, which is the machine layer. And so because the PMAP in this illustration is just this blob, then really think about it in object-oriented terms. It's entirely abstract, and you can basically replace, just like you replaced it from Intel or PPC to ARM version 7 and then to ARM version 8 and onwards, you can also replace it so that it goes to, well, somewhere else. Now, just to remind you why physical memory is important. Physical memory is kind of like the latest battleground at this point, because once you've got KTRR and you've got PPL, then you have to eventually find all sorts of physical memory faults. The last known jailbreaks in iOS 16 hinged on that. There was one actual KTRR, sorry, not KTRR, actually also KTRR, full bypass, which was Project Triangulation, if you recall that, which enabled you to basically override any of that stuff. But with the exception of that, all of the various techniques that are discussed now are at the low-level physical use after free, what they call PUAF and stuff. So there's the groundbreaking work by Felix PB, and there's also another post by Ian Beer at the time from 2022, I want to say. And so the idea is you basically have to work at the physical level, because the physical level is what really happens. When you allocate a virtual memory page, that virtual memory page, first of all, may actually not be allocated, right? It could be a lazy allocation, which is what's shown here. If I could find my mouse. Where is my mouse? Hello? Oh, there you go. Yeah, so this is basically those lazy allocations, and then they don't take up space. But then if they are pages that take up space, that's when you can do all sorts of physical memory tricks. The most common one to us is, of course, the idea that we can share them. So whenever these arrows are cross-links, it's basically shared pages that are seen both by address space 1 here and address space 2. Best example of that, of course, is the DYLD shared cache. But really, unbeknownst to most, if you're looking at any type of inode and you're doing a double mapping, for example, running ping twice, that too is implicitly shared. Only the readable, writable obviously can't be shared, and that's when you get all sorts of tricks like copy and write, which you really, really hope is clean and not so dirty. Now, the TLDR, again, why do we even bother with this? Is because physical memory plays a key part in our discussion here. This whole idea of first the PPL and then GXF is all boiling down to providing a separate, compartmentalized way to access physical memory, and that eventually culminates in what they call SPTM, which is a secure table monitor. So we'll see that. Now, again, going back to PPL, which was back, I remind you, in iOS 12-ish and the A12 and higher. So we're looking at a new feature that basically is working in tandem with KTRR. The KTRR portion is just to lock the text and the data const up until a certain last. And then what we have with APRR is we have two other registers, again, custom Apple Silicon. And so it's S3 something something and S3 something something, where we give them the name of reg APRR EL1 and EL0. These names are given by Siguza, who ended up providing an amazing write-up on this. Somehow, luckily enough, 2 days before Ivan Kirstik went and talked about it in Black Hat, so basically stole his thunder. And what it is that those registers are there, and you can set them basically whenever you want. But there's a novel way with those registers, is that what they do is they give you bit masks that apply over the page bit masks. So again, going back to here, you're seeing this as a logical view. But in the physical view, there is what we call page table entries. Every physical page has an entry that is shared or communicated from the kernel to the MMU This basically is where the kernel says to the MMU, these are the protections I want on that page, read, write, execute. Only in the case of PPL, Apple has this really, really novel idea. They say, take those 4 bits that we would use. That would be the access protections, which are 2 bits. And we've got the PXN, which is privilege, execute never. And we've got XN, which is literally execute never, not just in privilege. Then what they do is, don't think of them as these 4 bits. Think of them now as an index into some type of table. The table is housed in those registers. And it's separate registers here for user mode and for kernel mode. Now, when I said you can set them anytime you want, it's assuming there's no remote code execution or any type of, either in user mode or in kernel mode. Because if you can do that, then you can start toggling and fiddling with that. So that's still a problem. However, let's say you can't. Then now the kernel has PPL segments, which right off the bat are read-only. But then under a certain trusted path, they become read-write. And this forms the substrate of the so-called read-only zones. Like, for example, now IOKIT entitlements, or like the UBC blobs, or basically any zone up until AMFI OS entitlements. So I want to say from zone number 3 to zone number 14. It's your proc.ro, it's your threads, all the good stuff. Now, let's say the kernel needs to allocate a new proc, so they do that with proc task. But then some immutable stuff, like, for example, your chaos cred, which is not going to change. It's your effective UID, GUID, and such, or real UID. That's only going to change, if it ever changes, under set UID. So it's only under a particular code path. So now that code path has to go and ask for the PPL to flip those register permissions, and suddenly the page becomes writable. Ditto if you're allocating something in zone memory. So now you've got a Zaluk, but you also have a Zaluk RO. Zaluk RO goes through that path and actually writes something. And so your CS flags, your code signature flags on the process would be there, or your task flags that tell you if pack exceptions are fatal or if you're a platform app and all that jazz. That's also going to be there. But then once your process is created, that's it. We're not touching them anymore. And there's no way, let's say, for example, I did have a quote-unquote kernel arbitrary read-write. I can't do that. Because unless I open the gate, and then I'm able to patch normally, then those pages are essentially, the MMU would block me. The AMCC, or in general, the MMU, will basically give me a bus violation, which will lead to a kernel panic, and therefore it's basically game over. Now again, I want to emphasize, if you could somehow find a kernel code exec, then it's all basically moot. Because then you could simulate the exact path of saying, you know what, I want to free that zone element. You know what, I want to add more entitlements, in which case, we're back to the days of iOS 11. Now, this is such a strong feature that even ARM, I'm not sure if they were inspired by it or because it's cross-pollination between ARM and Apple, who I think is maybe still a shareholder even. They have something called in ARM version 8.8 or version 8.9, feature S1.2, depending on stage 1 or stage 2 translation, PI or POE, which means basically permission indirect or permission overlay extensions. And that's effectively the same thing, but now it's in the ARM spec. What does that mean? That in about 2-3 years, you're going to see it in Android as well, and that obviously is going to revolutionize things. Because again, to remind you, right now in Android, even with their so-called trust zone, it's still trivial to, once you get an arbitrary kernel read-write, use it as such. In other words, you can write anywhere. And it's actually even worse in Android because of K-probes and ftrace and stuff. You have the kernel to be readable, writable, executable all at the same time. So that's APRR for you. And then now PPL becomes this substrate, because if we have this trusted path, suddenly a myriad, a universe of opportunities opens to us, right? Because we can use it in the read-only zones that I've mentioned. And then we can do all sorts of, the proc.ro and the CS blobs in the sandbox. And then those arbitrary kernel read-write primitives are effectively gone. Now, it's not to say they're all gone. They're still, writing into calc data or into calc with whatever subtypes. But yeah, they do all sorts of other mitigations like sequestering and like all sorts of subtypes of ALEX, which are meant to make things harder, and they do, in fact, make things harder. And then that also enables other features that later mature in iOS 16 4 years later. For example, the above-mentioned developer mode and lockdown mode, really, which was left out of the slide, or what they call in iOS 18 REM, which is restricted execution mode. And even better than that, they can extend this thing to user mode, because remember, we've got this register here in APRR like this, right? But there's also one that applies to EL0. And there's additional registers that enable you, but that comes with SPRR, that enable you to do JIT, and that enable you to do what they call later TPRO, which is trusted path read only, which is basically that they can apply that to DILD so that you can't overwrite DILD's memory, or you can actually make this same read-only zones apply to a user mode allocator, which of course is undocumented only by Apple. In order to effectuate this, they have to go through SPRR. And again, tons more registers. In this case, it's SPRR config that we know about. The other ones, we don't really know the names. Sometimes, maybe I shouldn't be saying this, the names leak through the tests that they leave in XNU. So under XNU's code path, there's tons of these little tests that are actually very useful. And so we know of some registers. There's obviously some here that are unknown. But then that enables us to do all the JIT. There's one typo here. This is EL0, not EL1. And basically what it is that this enables you to gate those permissions on, for example, a JIT page, a just-in-time compilation, to allow RWX to be enabled and then disabled and then enabled again whenever you want. And there's also an API that's used by libpthread that you can actually see, although the implementation is, of course, opaque. It's like not shown, but you do see it as a header. It's called OS-thread self-restrict, which literally means that the thread itself says, I want to restrict my access to this region to be read-only, or to be RWX, or again, later TPRO. Now, with the abundance of models, how do you know if it's even supported? There's an OS-thread self-restrict is supported, which really reads the COM page, which is exported by the kernel, and so that's that. The last thing, before we go into GXF, so we'll go back a step after this, is MTE or MIE, which of course is the latest and greatest. And you read Apple's blog, you're looking for like hardcore technical analysis. All you're getting is, oh yeah, it's a culmination of like unprecedented design and spanning half a decade. Why did it span half a decade? Because ARM introduced it in version 8.5, and it took us literally half a decade before we decided to implement this, right? Because it's basically the same thing. Now, in their defense, they did wait for eMTE, as they call it, which is MTE4, which is really ARM version 8.9, but it's still been around in Android for a long, long, long time. And MTE is supposed to be the game changer, again, until somebody like Brandon, who apparently is out in the wild again, might have something to say about that. But for the most part, it's probably going to have, a bypass or two, and then it's going to settle into the same form of pack, which in kernel is very secure. MTE, for those of you who are unfamiliar, is basically a simple idea that just like in pack, we repurposed whatever TCR EL0, like 24 bits or so, 23 bits or so for the keyed hash of the pointer. Here we take 4 bits and we put some memory tag. The nice thing about MTE, though, is that unlike pack, which requires you to opt in, and as another tip, opt in now. Critical applications on iOS, that are third-party, like, I don't know, well, WhatsApp and maybe like Signal and stuff, they're still, ARM64. And that's absolutely terrible because there's no pack. And then if you find a vulnerability in WhatsApp, it's very simple to ROP-JOP like it's, 2012 again, right? So in that respect, if you've got pack, that does a great deal to work with the pointers. But then those are primarily for data pointers you have to explicitly sign, and for instruction pointers, again, you have to explicitly sign. That's why you compile for ARM64E rather than the normal ARM64. But then, in terms of MTE, this is something that the kernel implements for itself, and this is something that libsystem malloc implements. So you guys use the malloc, valloc, realloc, free, and all that jazz. That's going to be handled transparently for you, and you won't even know there's MTE. The one caveat is if you're doing your own mmap, there's probably going to be some flag. Apple hasn't released the sources. I'm pretty sure it's going to be VM flags MTE or something like that, but no, it's redacted. God forbid that we would know. But eventually when the sources come out, you'll know about that, and it's basically just the same thing that's been going in Android since 13. Apple is very, very strict about the UX, and MTE does have a performance impact. If you read through their blurb, they're going to tell you, yeah, we managed with the performance impact. Whether they did or not, time will tell, and that's basically only available in the A19. So you're looking at the iPhone Air or the Pro and stuff. Now we're taking a step back into GXF, which is the guarded execution feature. This is something that's available from the A15, which, if my iPhone math works, is the iPhone 16 or the SE3 or those types of devices. Now, this is a new feature, and again, this requires Apple's silicon modification, and this is, unlike MTE or PAC, a custom feature. Not only that, it's very unlikely you're ever going to see this in the ARM specs because it basically neuters the whole point of EL3. Like if you've got this and you don't really need trust zone, it's very similar in design. Registers, you've got all of those, and honestly, you've got a lot more of those, right? But the key point to note here is that they have a striking similarity to the EL registers that you may know. So exception level registers, right? So you've got the V bar instead of the EL1, EL2, or EL12, or EL3. You've got GL1 and GL12, and of course also GL2 that didn't make the slide. Fault address register, save program status, et cetera, they're all here. And so what happens here is that these, again, are all in the implementation defined space, S36 something. And what you do with them is you create a separate, I can't say exception level, so I'll call it a guarded level. Now, all of basically what we know about this stuff is, again, due to the pioneering work of the Asahi people, which I should have said something about. Wait, yeah, I think I must have skipped through that. But basically, back in APRR, there is a project called Mini. There it is. And Sven Peder of Mini is basically responsible for everything we know about this, because he's of the idea that Macs should be able to run Linux. Okay, I know it's terrible. Okay, I'm not saying anything, but still, to each their own, but he wants freedom. And in this freedom, he actually goes and reverses stuff. He opens your Mac up, your Mac Mini or your MacBook, and in the firmware configuration utility, you can say any software trusted by Apple, anyone trusted now, which is like a Tatsu GS Applecom ticket, or you can say whatever, any software I want. Once you do that, iBoot can load anything, and so he loads his own custom kernel from Linux, and he does a great deal of reversing, so all of the stuff we know about the SPRR registers and all of the stuff we know about GXF is basically thanks to him. So he dubbed the term of GL0, GL1, and GL2, where this is essentially the secure world of ARM. So in the ARM case, you do like go to SMC, that goes you to the monitor, it transfers you to the monitor, and then from the monitor you can have additional run levels that are EL0, 1, and 2, but are secure. Okay, they also do that in ARM realms. In this case, we just call them GL0, GL1, and GL2. There is no EL3 or GL3 for that matter, because remember, that was an attempt that they did and they're off, they don't do that anymore. And then in those different realms, we can now have different components. What components are those? We've got the TXM, Trusted Execution Monitor. We've got the Secure Page Table Monitor. And of course, we've got exclaves that my predecessor Luke has just explained or mentioned, and I'll be explaining some more. Now, the mode traversal here, there's no SMEC or SMC, but there is a special instruction, which we call genter. And genter is this instruction, which is 0020142, and then something. That something is an immediate, and it could either be a 2 or a 3 because the immediate is a 5-bit here, so it just doesn't go well with a hex, whatever. And then you do what you do, where you do a genter, you can pass the immediate value from effectively now 0 to 4 is the only ones to use, and you get teleported into this alternate parallel universe, basically, that's a secure guarded domain. Once you're done there, or rather I should say once they're done there, they do a gexit, which is akin to an ERET. And in gexit, there is an immediate, but nobody uses that immediate. So I've seen everybody use, ChatGPT for this, ChatGPT for that. So I'm like, you know what, genter? I want to see what they know about this. So I asked ChatGPT, what is Apple Silicon's genter? And it goes, there might be a confusion or a typo. I want to help you, but you obviously don't know what you're doing, blah, blah, blah. It could be a neural engine thing, or this, or this. And I'm like, okay. And then somebody tells me, hey, man, look, come on, you're killing ChatGPT. You should try it. It just needs the context. I'm like, dude, I told Apple Silicon, right? No, he says, say the context. So I'm like, okay, put this in more context. And I'm like, you have no idea what you're talking about. Genter is a custom instruction in Apple Silicon. Now, thankfully, this is recorded. So if ChatGPT, like, in a while develops, like, self-awareness or something, this was a joke, okay? Do not kill me. Do not send me. Do not tie me up in tubes and feed off of me and leach my bioelectricity. Please do not. I did not mean that. It was a freaking joke. But you know what? Maybe that's not going to happen so soon, because then it goes, oh, I understand. And I'm like, okay, whoa, get ready. So it says thinking. And then it says, well, of course, it's general purpose entropic random generator. It's a specific instruction that, and I'm like, whoa. And like, what? And like, yeah. And then just to make sure that it's not playing mind tricks with me, I tell it to say, show me how to use Jonathan Levin's disarm tool. And then he creates all sorts of like crazy switches, which actually make a lot of sense. But I'm like, wait a second, did I write this? Did I actually introduce this? It kind of makes you doubt your sanity. It's like gaslighting on a totally different level. It's like GPT lighting, whatever. So I'm like, you know what? You know what? Maybe the machine apocalypse is not upon us yet, and maybe I should just short NVIDIA and short Microsoft right now. Although I can't say whoever runs ChatGPT because they sponsor here. So but yeah, and also they're publicly held, so I can't touch them. Anyways. So now with all this in mind, let's talk about SPTM. We've got this genter, which obviously is a custom instruction dude, or machine, or whatever. And we use it to enter a new execution mode, and something has to rest there. So again, separate between two things here. There's the hardware, where genter lets us in and out of this mode. But at the end of the day, there's got to be software. And this is still on the same AP. This is still on the same application processor. It's still on the same core. And in fact, you can have different cores running in different states, some of them being in GL, some of them being in the normal mode. So you're in here, and you're in the secure page table monitor. This is naturally an IM4P. And we've got Blacktop here somewhere in the audience, so he's got his IPSWA tool. You can also just do it directly with Disarm. I'll do a quick thing here where I open up a terminal, if I can find my terminal. Where is my terminal? There you go. Yeah, probably here. So if you look at the documents, what is it? Sorry, downloads in my case. Downloads, firmware, and over here. So you've got in 19, which is really 26, I know, whatever. Then you've got here the firmware, and you've got the TXM and the SPTM. Oh, sorry, you're looking, sorry, now you can see it, okay? And so you've got the TXM and the SPTM, along with their companion files because I ran some analysis on them. And then disarm of, for example, SPTM. So actually before that, as an image 4P, it looks like this, like head. So you can see here like an image 4P and the standard BVX2, which is Apple LZFSE. But then, with disarm, you can just go directly and expand it, and like disarm -L shows you, yeah, that's what it looks like. So it's a Mach-O. It's a Mach-O that's basically its own self-contained, not RT-Kit for a change. So, it's still self-contained. It's still like running in its own execution level and has no dependencies. So it has to pack its own libc, but it's running in GL2, basically. Okay, so that's your SPTM. Another thing you have here is, of course, TXM, which is this little guy. And again, it's the same exact thing where if you do like a disarm, -I, -L, -whatever, it tells you exactly what it is because it's just basically a Mach-O. And why is it a Mach-O and an IM4P? IM4P for the signature and for the ticket. And the Mach-O because, it's iBoot. Come on, iBoot is a one-trick pony. All it can do is load Mach-Os. Now, there's a wonderful, wonderful paper that just got dropped 2 days ago. I think also by Darmstadt people. So Lucas was from Darmstadt. I think also these two people. Really brilliant work, really heavy, detailed design of everything, like analysis, teardown. Really highly recommended, and it's hyperlinked here. And one thing that I realized after reading that paper 2 days ago is like I've been an idiot because Apple leaks so much of it, not in the kernel sources themselves, but rather in kernel framework. Go figure. Kernel framework is something that they spin off of the export headers of XNU, but unlike the export headers of XNU that eventually somehow in the open sources get redacted, this one they don't. So there's a plethora of information. It's almost like they want to document this. Okay? Now, in this case, GL2 is able to be transferred to or moved to from either the non-GL, and this is where the genter instruction sets ESR GL1, or through GL1, and that would be SVC exceptions, or, sorry, this is GL0 and GL1, my bad. I just did add this recently. So it could be GL0 from SVC exceptions, or it could be GL1, in which case GL1 is already running in supervisor, so it'll do an HVC, and that's what they call the SK, or secure kernel. So it's, again, a CL4 type thing like Lucas just mentioned, albeit differently. Now, you can actually see the exact code, which I'm running late on time here, so I'm not going to go through this. But long story short, there's this register and there's this register, which I dubbed genter adder and then genter error maybe, because this one actually they load a tight loop there. So presumably if something fails, they want to debug it. But genter adder is where they can set their own entry address, and then basically whoever in kernel mode or anywhere, in the non-world, non-secure world, the non-guarded world, does a genter, that automatically teleports you here.
And then you also have here the do genter, and you can see that the genter 0, 1, 2, 3 get into the exception syndrome register in the lower bits, which are the 1F. This is all annotated directly and automatically from disarm, so excuse the indenting here. And then you can see that on number 4, it's like, I called it then XNU, what a terrible failure. It turns out in the headers, it's like XNU panic begin. Good enough, same thing. And then you can see right here, genter 0, that would be from XNU, or you can do genter 1, or genter 2, and genter 3. So these are basically the way where XNU can communicate with those other components. Now, a key point here is dispatch tables, where you've got the SPTM domains are XNU in domain 1, TXM, which we'll see in a second, domain 2, and SK in domain 3. You also have another domain for hibernation. And then you've got a bunch of IOMMUs. IOMMUs are meant for cross-processor attacks where, say, for example, Lucas was saying the C1X. Some of you will maybe pwn the C1X and get the $1 million. If you do, there's better money to be gotten elsewhere, but whatever. But long story short is that, okay, so what happens if you get baseband execution? Normally, you do all sorts of DMA tricks and then get kernel execution, or kernel memory read, right? Which is kind of like what Gal Bignamini did on the Broadcom firmware back in Project Zero, with a complete write-up for iOS 10.3, but nothing for Android somehow. Wondering why. It's like, Broadcom doesn't use Android? No, they do, whatever. Anyway, so here what you see is that you've got the SPTM domain that's gonna go here, you've got the SPTM dispatch endpoint that's gonna go here, and that's gonna go in an argument to x16. Why x16? Because it's kind of like, popular. It's like what they do also to do the ABI to get into in an SVC. So you can see those very easily with gadgets, and you're doing a disarm -G, move K, move K, move K, and B. And you can see that all throughout XNU, there's like all these move Ks where they set the immediate. There's actually more subsystems here. It also does subsystem 6 for the darts and whatever, but I just showed you one example here. You can find all of them. And all of these funnel to function 29.190, whatever, which is this thing, and that reps the genter. Again, I always suspected these are like callouts. It turns out they're called post and pre-entry hooks, thanks to the kernel framework. And that gets you into SPTM. Now, what do you do in those methods? You replace all of PMAP. So you've got a full table here, which was added to in Darwin 25, and really all sorts of stuff that has to do with maintaining page tables. And the gist of this is that whereas XNU was once able to see its own page tables and to edit its own page tables, that ability is now gone. XNU can now only say to the SPTM, hey man, I need you to map this page. I need you to unmap this page. I need you to do a share on this page. I need you to move this, et cetera, et cetera. So this is literally extirpating all that code of the PMAP and just basically turning it into little shims that become effectively SPTM shims. Key in this is that now we have logical typing. Now this is not MTE, this is actually even better. Because at a page level, SPTM, when you map a page or move a page, it's going to say, wait a second, there's like 64 page types. You got to decide which one you want. And there's like a crazy state machine that, again, the above-mentioned article from the Darmstadt people really explains in a nice flow graph, so you should check it out. And then what it is it tells you that some pages may be changed from ownership of XNU to ownership of TXM or to ownership of SPTM or SK, and you have to do that under strict rules. Now, the pages are, the states, excuse me, are here. You can see all the states like hard-coded as strings because there's a state to type ID, state to string and a type ID to string. And in type ID to string, it's very easy to see that you've got these types. So 10 or so for SPTM. XNU has a ton, which I've left here and I've annotated because I realized at this point I'm not going to have time, so I'm going to share these slides anyway soon. But you can also see that in the new one, there's like tag storage so that MTE is like owned effectively in a separate compartment, because otherwise you could overwrite MTE. And there's all sorts of other stuff that we're not seeing yet, like restricted I/O and restricted I/O telemetry. TXM has its own things, and SK is, as a microkernel would be, very, very like elegant and only for regions. Now, there's also a libSPTM, and libSPTM is kind of like an in-between bridge. So if I still can do this and not anger the time gods here, I'll just, I think I already have this here, yeah. So do I have the sim? I know I have the sim. So there's SPTM args, which is somewhere here. It's just so hard for me to see, sorry. So if you look at the SPTM args like this, right, you want to dump this, right? And so, oh man, I thought if I'd be pro, it'd be better, but apparently pro is not good enough. I'll do basic. Okay? So if you go here and you dump this particular region, this is the SPTM args, and that's a bug in the terminal. When you change the thing, it just, the scroll bar, it all messes up. Okay, this should fix it. Yeah. So when you dump this thing, and I'll just dump it, I'll just dump like, 384 of these, then you can see that it's got this region with a RAN seed. This is also referenced by the libSPTM H file in SPTM common. And you can see that there's this mix of addresses, some of which are owned by SPTM, like this one, for example, and some of which are even physical. These are physical addresses. So SPTM communicates the root page table, but nothing more. And over here, there's the SPTM version, and this is all of the SPTM data itself, which you can easily see if I'll dump, lib SPTM state T at this address. What is it, 90 we said? Yeah, and that's what it is. So it's currently up at version 7, and you can see all the frame table and, what panicked and what the state is, and so forth and so forth. Now, in terms of TXM itself, I'm not seeing Andy, so I'll just go on a bit, right? So TXM is basically where you've got this code signing monitor. The code signing monitor is now laced all over the kernel in relevant places where I'm not connected to the internet. But what it is that they do a CSM prefix that can be dynamically changed to either PPL or to TXM or to XNU. There you go. And this is where you can see that in this new cross-reference, and that way they can move from different devices in different configurations. What they do then is they take a TXM selector call, which is basically this structure, and in this you can pass arguments in and out of trusted execution mode. The parameters go on the stack, and then you've got an example here of TXM kernel call. What it does, it calls the internal, and then you've got here the example of get trust cache info, that's called. And let's just again another quick example. If you're to look at documents, downloads firmware 19. Firmware, right? So if I do, for example, a dump, disarm rather, of, trust, cache, runtime init, then it's really easy to see how these things are implemented, right? Sorry, not in this, but rather in the kernel itself. I need to do it in the kernel itself, so that will be, where did I put the kernel? Here. And so we want to do it here in the extracted kernel. So if you do that, you're going to see, there you go. You see the panic messages of AMFI. These are the same panic messages that you see here, right? And then you can actually see the TXM kernel call where they load the selector. It's really easy to see because you can see the structure like basically one by one. The selector always goes in the beginning, then the number of args, and you can see how they're basically building this entire struct here at offset 0 relatively, offset 6 relatively, and this ties in to what you can see over here as well as offset 0 and offset 6. All of this bridges obviously to TXM enter, which is this thing, and then all it is subsystem 2. So this is domain 2, and that's that. And the interface is everything that AMFI used to do. So right now it's working in conjunction with that despicable AMFI, where you've got the dev mode that's there, the provisioning profiles, obviously the code signing, obviously the JIT, and of course the crown jewel, which is entitlements. Per the interface from TXM back into SPTM, it will call an SVC0 with a subsystem 1, and there's only 4 endpoints there to lock itself down, to register its dispatch table, yet again to do page typing, and then number 4 is like something that's related to user address spaces. Because the idea with TXM is you give it the address space of the task, or maybe even possibly an entire virtualized domain, and then it can apply code signatures on that. Again, there's an example here, but I am running out of time. Am I still good? No, I'm not still good. Well, so I would have done exclaves, but I'll talk about this some other time with people who want to talk about me if it is. Again, TLDR, the exclaves are with a secure kernel with an HVC, and an exclave CTL trap that goes and bridges you out, again, through a genter. The genter here is basically the same thing. Do I still have time? I knew it, sorry. See, I was prepared. But then, what I will say is that there's a long overdue blog post by my colleagues, the defenders, that already have the other blog posts on SPTM and TXM, so there's going to be one. It's going to have the companion files that I'm using, and it's going to have matcher rules, so you can auto-analyze any future version of SPTM and TXM and get all the symbols. The license is free. Just give credit to DFF, give credit in general, don't steal other people's work, and spread the good word. This presentation is already here So until he starts shooting you with his Nerf gun, you can copy this. You can copy this and use it now. And we don't have time for questions, but I do want to say I'm not coming back to Darwin. This is a one-off for him. And he's awesome, and thank you. And honestly, I have to admit the training was fun. And Andy, wherever you are, you're awesome. You didn't shoot me yet, that's good. Okay, and seriously, you fucking rock, people. So thank you so much. Okay. Any questions and stuff? I have to go. Okay. People, we're short on time, thank you, right? So any questions and stuff, I have to go and vacate the stage, but I'll be happy to take your questions. And I'm also here during lunch with a couple of books. Ta-ta.